So like I said, exam 3 scores were really good. I did have one general comment. There's something that I saw a lot. I'm not really a stickler for units. You know, I don't make you carry your units through the calculations, but you totally have to put your units on your answers. Okay. I'm not even sure how I feel about that, except that every class you'll take in the future and on the AP test and on anything else, you're going to lose a lot of points if you don't do that. So, so this is important. Okay? I don't wear my glasses when I bike, and I drove today, so. All right. So what are we working on? We're working on the work energy principle. Does anyone have any questions about the test before I go back to this stuff? Okay. If you have any questions about how to do the problems or how it's graded, or if you think maybe you should have gotten more points or something, just come talk to me as soon as you can in the next week or something. Okay, work energy principle. We're thinking about it in this form. The work done by all non-conservative forces is equal to the change in kinetic energy of the object plus the change in potential energy of the object. And it makes sense if you remember that the change in potential energy is equal to the negative work. So then this change in potential energy is actually the negative work done by the conservative forces. And then if you add that over, move that over to the other side, you end up with the total work by all the conservative and non-conservative forces equal to the change in kinetic energy. Okay, so let's do some examples. Anybody have any questions about the problems related to the work energy principle? Okay. So let's say there's a hill and an object with like a cart with a mass m starts at the top. Wait, I didn't want to do this one yet, did I? No, sorry. Let's save that one. All right, so we did the one with the skier. So now let's do a similar one, just a simple. Did we do the one with the spring yet? We haven't done a spring yet, have we? Okay. Okay, so let's say that we have a mass m attached to a spring with a constant k. And let's say that the spring, the object is pulled back a distance this way, L from the spring's resting length and release. So the first thing we want to do is figure out the speed of the object as a function of x. And the second thing we want to do is think about at what x is the object moving the fastest. Actually, let's do one more. At what x is the speed 0? Okay. And so this problem is meant to help you understand the way oscillating objects connected to springs work in general. So we're going to pull this spring back, pull this object back this way, and let it go. And if it doesn't lose any energy due to friction, it's just going to go forever back and forth like this. Okay? And so we want to figure out a function telling us at what x position, like you give it an x position, and this function is going to tell you what the speed is. Okay. And we're going to do that by using the work energy principle. Okay, so let's think about, the first step is to think about what forces are acting on this object. So what's acting? Yes, good. What else? Normal, good. And then the one that this whole problem is about? Yep. And we can think of that as K delta L. But anyways, so now that we know what all the forces are, we can think about what are the conservative and what are the non-conservative. Are there any non-conservative forces? The spring and the weight are both conservative. Those are the two kinds of conservative forces. Those are the two that depend on position. There's one non-conservative force, normal force. And remember, the normal force isn't going to do any work, so that's an easy one to deal with in this. In the work energy principle, that's not going to show up. And then the conservative forces are mg and the spring force. The non-conservative work, the work done by all the non-conservative forces, is equal to 0 because normal forces don't do any work. Anyone remember why that is? That's right. It's perpendicular to the velocity at any instant, and any time that happens, the force isn't doing any work. And then for the potential energy, due to the weight, the gravitational potential energy, that function is mgh. And we can choose a height to represent our zero height. So what do we want to choose in this problem as our height equals 0? Yeah, since it stays the same height the whole time, and potential energy only comes into the work energy principle as a change in potential energy, let's just choose it equal to 0. It'll never even show up. Yep.
So instead of doing that, can we just say that it doesn't matter at all because it's perpendicular to the velocity?
Yes, you can say that in this case. Yeah. I think the way to think about potential energies, though, is just think about the locations, and think about work that way when you're talking about non-conservative forces. But with the potential energies, just think about the locations at the instant 1 and 2. Okay. But yeah, you're right. That is how it works. Okay, so we're going to choose H equals 0 at the ground. And then the potential energy for the spring force is equal to 1/2 K delta L squared. That's moving in the x direction. Those delta L's are all along the x axis. So let's choose our x equals 0 location, or the origin. Choose the origin at the spring's resting length. And then if you do that, the spring potential energy is equal to 1/2 K x squared. Do you see how that works? Since delta L is a distance from the spring's resting length, and we chose our x equals 0 location to be at the spring's resting length, then any x value is just telling you how far you go from the 0 position, from the resting length. There is the issue of pluses and minuses, but since delta L is squared, it doesn't matter. Delta L positive or delta L negative, you get the same thing when you square it. Okay, so now let's go to the work energy principle. There's no work done by non-conservative forces. At our later instant, we don't know what the speed's going to be. So that's just 1/2 mv squared. Our earlier instant, our instant 1, is going to be at the instant it's released. So what's the speed at the instant it's released? 0. And so our kinetic energy at instant 1 is going to be 0. And then potential energy, we have 1/2 K x squared. And what's the potential energy at our earlier instant when we release it from rest? Well, what we know is that we're pulling it out. We're pulling at a distance L, right? So at instant 1, delta L is capital L, so this is 1/2 K L squared. Everyone follow what I'm doing there? So this is the kinetic energy at instant 2. This is the kinetic energy at instant 1, and that's when it's released. So instant 2 is when it's at location x. This is the potential energy at instant 2. That's when the object's at location x. And this is the potential energy at instant 1 when the object's released. So now we just have to solve this. We can divide, cancel all the 1/2. And we get mv squared is equal to kl squared minus kx squared. Then divide both sides by m. You get k over m times l squared minus x squared. And so finally, the speed is equal to square root of k over m times times the square root of l squared minus x squared. Yep.
Wait, the first time you had it, x squared minus l squared.
I had to move it to the other side, just in the algebra.
I didn't.
Yeah, I'm going from that work energy principle relationship.
I saw the plus in between those as a equal
Okay.
sign, so we didn't know that.
Okay, yep. And I have it split up this way. So here's v as a function of x. I have it split up this way. Like, why did I separate out the square root of k over m? That's because that's related to the frequency of this oscillation. The object's position as a function of time so x of t is equal to, in this case, negative L cosine of square root of k over m t. Yep.
I have a question about the equation up there. It doesn't make sense to me because it feels to me intuitively like when the spring gets to its natural resting length, on that equation there, the velocity will be 0, but I know that it will keep increasing, so it will be oscillating.
L is when x is equal to L, that's when it is as far away from its resting length as when it was released.
Oh, so x is decreasing.
So when it's at its resting length, x is equal to 0, and that's where you get the biggest speed.
Okay, so x is decreasing from L to 0.
It's decreasing from L to 0, then it's increasing from 0 back to, so it's going to go, so the motion is going to look like this. Here's its resting length. Here's x equals negative L. Here's x equals positive L. It starts out here and just oscillates back and forth like this. Okay? If you look at that function, the biggest values for v are going to be when x is equal to 0, which means that it's going the fastest, whether it's going to the left or the right. It's going the fastest when it crosses through that resting length location. So that was one of the questions. At what x is the object going the fastest? when it passes through x equals 0, and that means that the spring is at its resting length. And what's the speed when it passes through x equals 0? The speed is just equal to square root of k over m times L. It passes through that resting length position, x equals 0, so this is x equals 0, going two different directions. But this says that the speed is the same going either one of those two directions. It's just the direction changes. The velocity is opposite. Okay? And then at what locations is the speed equal to 0? There are two locations where that happens. Yep, thank you. X equals negative L and x equals positive L. And you can just see that from the equation. To make the speed equal to 0, you have to make one of these two factors equal to 0, and the only way to do that is to make x equal to L or negative L. Any questions about that one? Okay, so let's do another one related to springs. And this one also involves conservation of momentum. So let's say you have sort of like a pinball. Let's say the mass is 0.1 kilograms. And the spring has a constant of 300 newtons per meter. And then over here, there's another ball that's a little bigger. This one's 0.2 kilograms. The spring is compressed 0.5 meters. Oh, no, 0.05 meters. 5 centimeters. And released. So what's going to happen, like when you pull back the plunger in pinball, that's a game old people used to play. It launches the ball forward when you release the spring. So that's what's going to happen here. This 1.1 kilogram ball is going to get launched forward, and it's going to smack into the 0.2 kilogram ball. What's the velocity vector of the 0.2 kilogram ball after an elastic collision? Okay. See if you can. So what we're going to do is use the work energy principle to figure out how fast the 0.1 kilogram ball is moving once it leaves the spring. And then after it leaves the spring, we're just going to do conservation of momentum to figure out what happens during the collision. So there's sort of two parts. The first one is the work energy principle. To find the speed of the 0.1 kilogram ball after it leaves the spring. And the second part is conservation of linear momentum for the collision. So part one, work energy principle. If you think of a free body diagram of the ball, when it's in contact with the spring, there's a spring force pushing on it, there's the weight, and there's a normal force. The non-conservative forces are just the normal force. So that means that there's no work done by non-conservative forces because the normal force never does work. The conservative forces are mg and the spring force. Okay, so let's think about the potential energy for the potential energy due to gravity. That's equal to mgh, and we get to choose an h. Choose an h equals 0, and we'll choose it to be at the ground. So through the whole motion, the gravitational potential energy is equal to 0, because h is equal to 0. Any questions about that? So now the potential energy due to the spring force, that's equal to 1/2 k delta L squared. We can choose the origin at the spring's resting length, or really it's choose the origin at the ball's location when the spring is at its resting length. And now we can put together the work energy principle. So there's no work done by non-conservative forces. After the ball is released from the spring, there's a kinetic energy of 1/2 times 0.1 times the speed squared. When the spring is compressed 0.05 meters, before it's released, the speed is equal to 0. So the kinetic energy is 1/2 times 0.1 times 0 squared, and that's equal to 0. So that's the change in kinetic energy. The change in potential energy is 1/2 times 300. So at the later instant, once the spring is released from, once the spring is no longer in contact with the ball, the spring, let's see, you can think of it as like the spring's already returned back to its resting length. It's no longer, this motion of the spring is no longer affecting the ball's motion at all since they're not in contact. So you can just think of this as 0 squared. But when it's released, at the instant that it's compressed and it's released, the potential energy is 1/2 times 300 times 0.05 squared. And so you get 0.05 v squared is equal to 150 times 0.05 squared. And you get that v is equal to 2.74 meters per second. Any questions about that one? Are there any parts of that that's confusing? Okay, so now we're going on to conservation of linear momentum. Yep.
Okay, so in the last part you did, when you put in the second term and you change for the first, like, the 0 and the change of potential energy.
Yeah.
What is that? Like
What that 0 is, so really what's happening is, you can think of it, maybe a better way to think of it is, don't think of it as x equal to 0. Just think of it as soon as so you're always isolating an object with this equation, just like you did with Newton's second law and stuff. And as soon as the object you're isolating isn't touching the spring anymore, the spring's potential energy is 0, no matter what the spring's doing. I represented it as the spring's length is returned back to its resting length. But I think a better way to think of it is just the ball can't feel the spring anymore, so there's no potential energy there. Okay. Conservation of linear momentum now. So before the collision, we have 0.1 times 2.74 plus 0.2 times 0. Those are the linear momentums of the two balls before the collision. And after the collision, you have 0.1 times v1 plus 0.2 times v2. And you can write this as, so 2.74 is equal to v1 plus 2v2. So v1 is equal to 2.74 minus 2v2. And we're going to plug this into the conservation of elastic kinetic energy equation. So v1 squared is equal to, what's 2.74 squared? Oh, it's 15 over 2. So 7.5 minus, what's 4 times 2.74? Surely someone has a calculator that can do this. What? Okay, 10.96 v2 plus 4 v2 squared. And then the elastic equation says 1/2 times the mass of the first one times its speed before the collision squared plus the kinetic energy of the second one before the collision is equal to 1/2 times 0.1 v1 squared plus 1/2 times 0.2 times v2 squared. Cancel the halves, divide everything by 0.1, and you get that 7.5 is equal to v1 squared plus 2v2 squared. So now substitute v1 squared in, so 7.5 is equal to 7.5 minus 10.96 v2 plus 4v2 squared plus 2v2 squared. So 0 is equal to v2 times 6, okay, yeah, 6v2 minus 10.96, yes. Okay. Okay, so divide, so the two roots are v2 is equal to 0 is one root, the other one is 10.96 divided by 4, so what do you get there?
Well, you should have 6 inside the
Yeah, okay. This should be 6, thanks. So 10.96 divided by 6. 1.826. The 0 is the velocity of the second mass before the collision, so we want this one. So v2 is equal to positive 1.826 meters per second, and then you can plug into any one of these equations to solve for v1. So you should get something like negative 0.92. So the first ball after the collision is bouncing back towards the spring. And you could calculate now, like when it hits the spring, how far is the spring going to compress before it turns the ball around. Just keep going back and forth, exchanging kinetic energy for potential energy using the work energy principle. Anybody have any questions about that problem? Okay, let's do more of these. Yep.
I discovered a bit of a shortcut, and I want to know if it's okay to use this on like tests. If you take the 2.74 velocity and you divide it by 3, you get the velocity of ball 1. If you divide it by 3 multiplied by 2, you get the velocity of ball 2.
That's because of these masses.
Okay.
So that's a
Wouldn't work.
right.
Well,
That would only work
yeah,
if
but I mean the ratio between them, because the ball 1, the
Right.
one ball is 1/3 of the mass.
yeah.
of the
I mean, it's 1/3 because the
Yeah, I know it's not always going to be 1/3, but if it was like 1/5, am I allowed to use that shortcut on the test?
I guess that's okay with me if you you know what, don't use that actually, because what I want to get you ready for is to show I want you to be ready to show people, like on the AP test specifically, what you're doing, have them be able to make sense out of your steps. And so you're right that there's something there that's useful, but don't use it, okay? All right, so here's the next one. Kid on a skateboard. And let's say the mass is 20 kilograms, and he's going this way. And he gets to a hill that's 3 meters high. So let's say before the hill, the kid is going 6 meters per second. Actually, let's make this 1 meter. I'm not sure that would even get to the top. So this kid on the skateboard is moving 6 meters per second before the bottom of the hill. What's the maximum work that could be done by friction so that the kid still reaches the top of the hill? Okay, so who feels like you are in a reasonable place to take a crack at this? And who feels like, oh, hell no? Okay. Anyone else? Okay. I like that. No? You want me to just go through it? You do want to do it. Okay. Okay, try it.
We don't know the question coefficients.
That's right, but you don't need it because I'm just asking you what's the maximum work done by friction. So you're just going to calculate this from the work energy principle.